Good afternoon, everyone. My name is Tanusha Ganu, and I am co-founder and CTO of DataGlen. And today I'm going to present some of the work that we have been doing as part of the workshop with my team, Siddharth, Mayuri, Prabhu, and Shubham, as part who helped me in the workshop. So I'll talk about multiple problems that we have been handling. The overall objective is improving the yield of energy resources, distributed energy resources, using AI-driven approach. So quick context about the problem. So as we know, the energy vertical is moving from the centralized generation and distributed consumption to distributed generation and distributed consumption kind of phenomena, where there are a lot of distributed energy resources in the form of solar or electric vehicle storage, which are coming in place. And that's adding a lot of complexity to the entire network of the way we generate and consume energy. So as an effect of this, there are different types of equipments which are getting connected in the entire system, like solar inverters, battery inverters, there could be electric vehicles. And there are different interesting business models and economical problems which are being generated as part of this. So what we do at DataGlen at present is we do manage and monitor different forms of distributed energy resources. So as of today, we have 400 different solar sites which are being managed in India, which includes the metro stations, hospitals, and other small and large plants, as well as we are doing a pilot project in Australia with an Australian utility, where it's a combination of solar and storage for 200 residential homes. So as part of the workshop, we wanted to try out some real-world challenges that we are encountering by using some of the technologies which have been developed by Microsoft team previously, and wanted to see how that fits in our use cases. So these are the typical challenges. So this is where the setup looks like. So there are different types of equipments, including inverters, battery storage, different types of sensors which give additional context information, like irradiation sensors, temperature sensor, energy meter. And typically at one particular site, if I'm considering, let's say, metro site or hospital as one particular site, there would be one data logger or DataGlen gateway, which is a single board Linux computer, which is connecting with these different types of equipment and doing data collection and analytics at the edge. It's pushing the data in the DataGlen cloud and basically doing a bunch of other portfolio level analytics at that. But typical challenges of IoT, intermittent network connectivity. So most of these sites are at remote locations. Many a times we observe that there is disconnectivity of network for hours or days at a time. And we cannot rely on cloud-based analytics for low latency control responses. So there are interesting use cases where we really need a low latency response, and we cannot expect the data to be sent from the edge to the cloud and make the decision on the cloud. So those are the kind of use cases we are going to talk about over here. So the first problem that we wanted to tackle was intraday forecasting for local generation and demand. So why this problem is important? So we want to look at optimal utilization of distributed energy resources. So take an example of a house where there is a solar, there is a battery storage, and there is a time of use pricing. So solar is generating energy at a typical time period of, let's say, 6 to 6 p.m., 6 a.m. to 6 p.m. There are constraints on the battery storage of how much amount of charging and discharging can happen. And there are time of use pricing. So there are different hours of day which has different pricing. So if we want to have the policy to basically reduce the overall bill for a consumer, what we need to do is accurate forecasting of local generation, accurate forecasting of local demand, and then optimization to comply with the policy. So typically what we do is we do have day-ahead forecasting, which is based on the historical data from the same location. We also take into account multiple third-party weather forecasting services to do the forecasting for the next 24 hours, how much amount of energy that would be generated. But many times, due to various different reasons, including the weather forecasting service itself is not able to accurate the forecast of the weather correctly, or there are issues with the equipment during the runtime, or there could be demand spikes because various reasons. There could be changes in the during the day, there would be changes in the actual forecasting of generation and demand. So we wanted to see how we can do the intraday revisions into generation and forecasting on the edge without going back to the cloud computing. So we looked at this problem as the regression problem, where we are taking into account the information from the day-ahead forecasting for the next few slots, as well as the, let's say at 10:30 I want to forecast how much energy that would be generated for next 2 hours. So I have information of actual generation for last whatever 3 or 4 hours. We do have information about actual generation which has happened during those hours. And for each of the look ahead, we have independent regression models. So here we basically tried, we have used existing algorithms which includes gradient boosting, random forest and other things. But we also wanted to evaluate how the Bonsai and Proton regression models work in this case. So the Bonsai and Proton models which are built by MSR team, those were mainly built initially for multi-class and multi-level classification. Those were not evaluated or tested on the regression models. So we basically tried those models for the regression problems in this case. And for each look ahead window, so for 15-minute look ahead, we have one model. For 30-minute look ahead, we have different model. One interesting point to observe here is we had tried LSTM and other approaches before. But the issue with the LSTM model is if you are doing the immediate look ahead, it gives you good prediction accuracy. But let's say if you want to look ahead after 1 hour, you have to fill in the information in between with your predicted information. And if there is an error, it just propagates and exponentially increases the error in the problem. So we wanted to have the independent model so that that problem is tackled over here. So these are some of the results from Bonsai and Proton along with the existing approaches that we had studied. So on left hand side, we are showing the root mean squared error on each of the slots. So x axis, it shows slots for different look ahead windows. So one slot look ahead, 2 slot look ahead. And as we can expect for the immediate look ahead, the root mean squared error is low. So the accuracy is better for immediate slots. As we go along the further slots, the accuracy slightly decreases. But interestingly, the root mean squared error for Bonsai and Proton is lower than random forest and gradient boosting in this case. And it's consistent or comparable in the case of 6, 7 and 8 hours look ahead time slots as well. And if we look at the model sizes on the right hand side, this is the log scale. So in case of Bonsai and Proton, it's using 4.5 kb of model size, whereas the XGBoost was using close to 500 kb of model size, and Random Forest was using close to I think 2 megabyte of model size for the same kind of results. So it gives significant reduction in the model size while keeping the accuracies consistent. So in this case, we use 60 days training data and 10 days test data over multiple different inverters, multiple different locations, and did the results. Feature dimensionality was around 35 seconds. So here is a quick demo on this. So we are looking at individual look ahead slots with different models which are built. So the training is done on the cloud. The models are deployed on the Raspberry Pi, which is sitting there. So this is the box. And basically the evaluations of the results are performed on multiple different locations. So I'll just go to the demo link to give a quick demo of how it works. So basically it's showing that we do have a day ahead forecasting, and depending upon the actual generation, the next 8 slots forecast keeps on changing. So so on the days where either because of the equipment failure or because of the weather changes, if there are variations which are needed, then it would accurately predict the next few hours, and the optimization, downstream optimization would basically work accordingly. So basically it would, till the end of the day, it would keep on changing the prediction accuracies. Yeah. So the advantage over here is the models are compressed, so it can easily fit on the low footprint and provide the faster inference. So it's taking around 10 milliseconds of time for the inference in this case. So the second problem that we wanted to look at is predictive maintenance for different types of energy equipment. So based on the study, there are different types of maintenance issues or costs which are associated with different equipment in the solar plants. So according to EPRI study, it shows that 50% of the costs on the O&M are associated with the inverters. So we wanted to look at inverters as equipment and how the downtimes are issues which are because of inverters. So this is the data collected by our own monitoring system. So there are 2 manufacturers, A and B. So for manufacturer A, we have 81 inverters, and the mean downtime is 2% in the manufacturer A, whereas in manufacturer B it's around 4.52%, and there is long tail on both the cases. So it's important that we identify the issues for fixing the downtime as well as for the warranty enforcement cases, so that the manufacturer can replace in case of issues. So here we actually, the problem statement is alert the engineer at least 2 to 4 hours in advance before the actual downtime while reducing the number of false alarms. So for every individual inverters, we have a bunch of parameters that we get from the individual inverters, which include different voltages, currents, and temperature and other parameters. So looking into this, we actually extended, use the approach which is being used by MSR team for looking at predictive maintenance for other industrial applications. So here we are looking at 120, so 2 hours window and sliding of 15 minutes. So we are trying to look ahead in 2 hours. So what we do is we do a feature sampling to identify that taking these individual data points in case. So let's say if there is a downtime at 11:10, so we consider a 2 hour window before that and try to check whether in this 2 hour window are we able to predict that there is going to be a downtime after 2 hours or 4 hours. So we have done different types of feature engineering to do extracting statistical features and FFT features along the sliding window of 120 minutes and stride of 15. And these features can be efficiently computed on the edge using online algorithms. And the challenge was data is very skewed or imbalanced, so we had to do downsampling on the positive or the right data so that we are able to take equal amount of the negative and positive examples. And these are some of the early results. I think we need to do a lot more experiments on this, but these are the early results where we are able to get a 90% recall while keeping the false alarms rate at 20%. So by 90%, this is equivalent to 97.4 hours of downtime that can be avoided or proactively addressed. And since the models which are used are decision-based models, it helps, the model is interpretable, so it helps in troubleshooting as well as for warranty enforcements. And the last quick thing that I wanted to show was the third problem in solar case. Most of the inefficiencies are because of the soiling or the dust which gets accumulated on the panel. So that basically adds to significant amount of inefficiencies in the amount of energy that can be generated. So this is the data across 230 inverters from our own data set. So as we see that if the panels are not cleaned, after 3 weeks it gives close to 8% of reduction in overall energy generation. So it basically accounts to 8% of, close to 8% of soiling losses. So again, we wanted to model this problem as the regression problem. So here what we are trying to do is a retrofit on how much amount of energy that should have been generated given the observable parameters. So the observable parameters are solar irradiation, module temperature, ambient temperature, and the time of day. And we are trying to predict how much amount of energy that should have been generated and looking at the residual analysis. And we do have a patent application submitted on this already. So we look at the residual patterns, and there are different types of losses which exhibit in different types of patterns. So if in case of soiling losses, we see that instead of residuals being random, they have very nice pattern where when its cleaning is done, it goes positive and over time it comes negative. And based on that, we can also quantify how much is the soiling losses exactly. So we do have existing gradient boosting regression models which are supplied on the edge, which is giving close to 20 kb of model sizes. We do experiments on Bonsai and Proton, and we wanted to see if those can be applied to further get the reduction in model sizes. Interestingly, we have not reached the accuracies of what gradient boosting and random forest is giving using Bonsai and Proton, and we did a lot of variations on those and tried to understand why those are not reaching there. So here is a quick observation where the actual data looks like this. So there are two features which are most important. X-axis is irradiation, y-axis is module temperature, and z-axis is the actual power. So there are different types of, so there is a linear correlation, or there are good correlations between some high-level attributes, but there is a scatter which is seen in the original data, which is being picked up by ensemble models and by weak classifiers. But whereas Bonsai being a strong predictor, it's able to predict the linear function correctly, but not beyond the scatter which is predicted by the weak classifiers, it's not picking up those. So it reaches 0.96 of R square within one depth tree and very fast. But from that 0.96 to 0.98, it's not able to reach.
So is it because Bonsai and Proton are much more geared towards classification problems rather than regression?
I think this is mainly because of the way weak classifiers, as in one thing is definitely in classification, these kind of cases would be directly avoided. These problems would not be there in classification. And we first time tried those on regression problems, but it is fitting well on our first regression problem, where there are, I think, such kind of scatters of, so I think there is a very peculiarity of this problem, where there are two features which are very dominant and there are other features which have impact, but those other features are not getting captured in some sense in these kind of models because they are low depth models and they are designed not to be working in the ensemble form. But in case of decision trees or random forest, even in random forest, it's requiring 250 random as in the ensembles to pick up those weak classifiers, which means that most of the classifiers are actually picking the strong signal and not the weak signals in some sense. So these are some next steps on all these three problems. On the first problem, I think we would evaluate Bonsai and Proton on more data sets, and we would be putting it in deployment for the pilot sites. For the preventive maintenance case, we have tried basically on one particular manufacturer. So we want to replicate and see if the similar type of features are applicable in other manufacturers' models. And also we wanted to see that for doing a weighing of downtime based on the, so there are certain downtimes which are 10 minutes downtime. There are certain downtimes which are like 2 hours or 4 hours downtime. So can we predict, do the weighing of downtimes based on the amount of impact it creates? And also increase the forecast window. So right now we are looking at 2 to 4 hours forecast window. Can we increase it to 1 day? And does it make sense? Does it really pick up the signal day ahead in advance? So those are the kind of things that we wanted to look at. And in auto cleaning control, we would like to continue with the evaluation of Proton to see if for these kind of problems, if Proton would be able, Proton has multiple prototypes. So if those prototypes can pick up those weak points or the, in some sense, anomalies or outliers which are already present in the data. So those are the next steps that we would like to try. And I would like to thank you for entire support from different teams in MSR, Harsha, Pratik, Naga, Vivek, Aditya. All of them have helped significantly in improving and trying out various approaches where it's not working. And we would like to continue with the collaboration in future as well. Thank you.
I have a question. So it seems like most of the things you're doing are actually pretty, I wouldn't say simple, but pretty sort of straightforward time series, signal processing kind of tasks, for which I feel like a machine learning type of thing, it's a sledgehammer you're throwing at this problem. Seems like classical, I'm not a signal processing person, but if I think of classical signal processing techniques for estimation detection should be much more compact and much better than throwing machine learning. So I don't know if you've thought about, any thoughts about those kinds of things. It might actually give you a much more, because you know it's a time series problem, you know the time series signature of what that pattern looks like. Say I'm looking for a square wave, I'm looking for a sine wave. There are like, well, I mean, I'm not the expert in it, but I'm pretty sure you ask a signal processing person, they'll say, okay, this is a Kalman filter, blah, or match filter, foo, or something. Right?
So we have.
I'm not sure why machine learning for this problem.
So we have kind of looked at few approaches for signal processing. I think one thing is in this entire, the way the equipments are working, the signatures are not common across all different manufacturers, and signatures are not, so the kind of signatures which we are looking into residual patterns, so those are the signatures which we are doing post-processing, and based on the analysis that we have done from the data, we are now identifying that those are the processings which are required. So having a common generic model which is applicable for different types of equipments and different manufacturers' equipments, I think is a challenging task over here, and that's where machine learning approaches like this are coming in place.
So I guess there's two parts to it, right? One is, I mean, I was talking to students working on similar with you. I think there's two parts to it. One is the signature synthesis, for which machine learning might be the right approach, and then there's the actual matching which you want to run at the edge. And doing machine learning at the edge may not make sense for this. You actually do the complex machine learning to run a time series signature, and you may actually want to split about like an offline-online process. Like what runs online might not be machine learning, what runs offline by machine learning.
Right.
And maybe that's a better architecture for some of these applications.
Yeah, so I think definitely I would like to evaluate those approaches, but even in this case, that is the way we are trying to segregate it. So the kind of complex tasks which require additional third-party information, as well as if you start looking at day-ahead forecasting, we don't want to push the day-ahead forecasting on the edge, because that requires multiple other sources information and looks at much larger amount of data from multiple years and seasonalities and other things. So that information, those are the kind of things which are computed in cloud. But when we finally push that information on the edge, the issue is that we need to make this signal, make this inference every few minutes, so every 5 minutes or every 15 minutes. At that time, we have to otherwise call, if we are using machine learning models, we have to call back to the cloud and get that information. So we are trying to separate out the problem in the sense that whatever requires additional information and larger computation, that's pushed into the cloud, whereas a very small problem, even in case of optimization, we do a day ahead optimization. Based on the day ahead information, we do the optimization, and only optimization revision works on the edge. So in some sense, there is a classification of what would run in the cloud end, but I think I would need to look into if there are other signal processing kind of techniques which would be helpful for this. I have not looked into that.
Okay,
Yeah, thanks.